These are the specific heat capacity notes. It will be helpful to have a calculator and the formula sheet nearby. So looking at thermal energy can transfer into or out of a substance. This transfer of thermal energy is called heat. And as we discussed earlier, exothermic and endothermic reactions we can also think of these as processes. So, an exothermic process, that thermal energy is released, exo being exit. And so, heat energy, which we use the variable Q for, heat energy is lost. So, it would be a negative value for the heat energy of that substance. And the temperature of the substance is going to go down. In an endothermic process, thermal energy is absorbed. And again, these are processes just because they don't have to be reactions. They could be exothermic reactions or endothermic reactions. But if we don't have a change to the chemicals, if we just have the transfer of heat, like water heating up on the stove or ice cooling down in the freezer, the chemical substance isn't changing. It's just that the process is that transfer of heat. So, an endothermic process, thermal energy is absorbed. That endothermic would be energy is going into that, and so that would be if heat is entering, that's an endothermic process. Exothermic heat is exiting. That would be like the ice freezing. Um, or water freezing to ice, energy is transferring from warmer water to the surroundings, and then the water is cooling till it forms ice. Endothermic is into that Q value would be positive, and so the temperature of the substance is going to go up because that heat is being absorbed or gained by whatever that substance is. So each substance has a specific amount of heat that is needed to increase the temperature of an object. And so when we're looking at how can we measure that, because it is going to vary for each object, how much energy is required, that is called the specific heat capacity, which we use a capital C as our variable. And so that specific heat capacity is the amount of heat needed to increase the temperature of an object exactly 1 degree Celsius. And so because we are looking at the amount of heat is measured in joules, needed to increase the temperature of an object. Well, that object, we need to know how much we have, so that would be mass. And then we're looking at changing the temperature. This is a measure of how much heat do we need to change 1 gram by 1 degree Celsius. And this value depends on not only the chemical, but also on the state of matter of that chemical. So for water, H2O, solid, liquid, and gas all have different C values. And this is the energy required. This energy is dependent on IMF strength. So liquid water's hydrogen bonding IMFs result in high heat capacity compared to other liquids, which plays some very important roles in how our world works. So, kind of looking at this, and we aren't going to use calories, we are going to use joules or kilojoules when we're looking at measuring heat in this unit. But calorie you probably recognize because that is another unit we can measure energy, and that's what we kind of the base of our unit for food calories. So we measure energy in food. And so again, this kind of shows temperature and specific heat. So if we are going to change, or if we're going to add 1 joule of energy, and we're trying to change the temperature of 1 gram of material, well, that 1 calorie is going to increase water's temperature from 0 to, this looks like approximately 1 degree Celsius with that 1 calorie, where something like steel is, with that 1 calorie, 1 gram of steel is able to change its temperature 8 degrees Celsius. And then we see gold, 1 calorie or of energy is going to change 1 gram of gold by 31 degrees Celsius with that. And so that definition or that value of specific heat is different for different substances. And so here are some examples. You won't have to memorize these. If we look at CO2 gas, this has a fairly low specific heat, whereas copper solid has an even lower specific heat. Same thing with iron. As we look though, then solid water, that is now above 2. Liquid water is at that 4.184. So that is a very high specific or heat value. And then water vapor would be 3.14. And we are going to focus on looking at energy changes with water. And so these are on your formula sheet. So you may need to use those. You may be finding a specific heat, but they are not things you need to memorize. So how can we use this value? But first, here's some information on the specific heat of liquid water, why it is important. Please go through and read that. Ask questions if you have any. It tells us a lot about how that water helps regulate those changes in temperature and that transfer of heat. And so we can then calculate magnitude of heat flow, magnitude being how much, and then we can find direction as we look at change in temperature. So for a pure substance of mass m, the expression of Q for that heat can be written as Q equals mass times C times delta T. And so that magnitude of heat flow or that thermal energy is measured in joules. We use the uppercase J to abbreviate that unit. The mass of our substance is measured in units of grams. C, that specific heat, we talked about those units. And then delta T is change in temperature. And this temperature is in degrees Celsius. Notice it's important that we have degrees Celsius, grams, and joules because those are what make up that specific heat constant unit. So that's why we have to make sure we have those correct units. And if we need to find a change in temperature is just final temperature minus initial temperature with that. And so this is on your formula sheet as well. And so we can calculate that magnitude of heat flow using information provided and that formula. So if we have 100 grams of 4 degrees Celsius water is heated until its temperature is 37 degrees Celsius. If the specific heat of water is 4.184 joules per gram times degrees Celsius, calculate the amount of heat energy needed to cause this rise in temperature. So with something like this, staying organized, looking at what we have, I like to go through and write out my variables, and then I can look at what is my question asking for, what things do I need to find? And remember with that delta T, that's temperature final minus temperature initial. And so we've got 100 grams. Well, 100 grams is a mass. So 100 grams of 4 degrees Celsius water is heated until its temperature is 37. So this is going to be my initial temperature. This is going to be my final temperature. And so I can do 37.00 minus 4.00. Remember, when we're subtracting, we look at digits after the decimal. And so we have 34, and then we keep 2 digits after the decimal. Degrees Celsius, that's our change in temperature. And this is a positive value, meaning that's going to result in us having a positive heat value. All right, and then I got distracted. So if the specific heat of water is 4.184, and so between 0 and 100 degrees Celsius, water is a liquid. So we have the specific heat of our liquid water that was given to us, but for water, it is also on your formula sheet. And so we have 3 of the 4 variables. So now we can find what is the magnitude of that heat transfer, which is what it's asking us for. Calculate the amount of heat energy. So let's find that Q. So I've got my formula up here. Q equals mass times C times delta T. I like to calculate my delta T beforehand if I can. and then I can just plug that value in, but you can always do that calculation within your problem just as long as you follow order of operations. If you want, you can rearrange your formula for your unknown right away. Luckily here we are solving for Q, so this is already organized so that we can just plug in our values. So we have 100 grams times that 4.184, and I'm actually going to include my units here. And then times my change in temperature, and that is a positive 34. And so that is going to result or tell us the direction of that heat transfer into or out of the substance in our final answer. And so then we can go through, multiply all those values together. So I'm multiplying 100 times 4.184 times that 33. Sorry. Let me fix that. And when we multiply those together, I get positive 13,794 for my Q value. Looking at my units on that, we've got units of grams here and in the numerator, grams here in the denominator. And so those units cancel. We have units of degrees Celsius here and in the denominator here. And so those units cancel. And so that's how we are left with that unit of joules on our answer. So now let's just take a look at our sig figs quick. I did this subtraction here, so now I'm going to just kind of look at what are my values of once I'm at that multiplying point. So I have 3 sig figs, 4 sig figs, and 4 sig figs. So let's keep 3 sig figs in our answer. We're going to keep the 10,000, 1,000, hundreds place. And so we would have positive 13800 joules. And we are going to see a little later, we often are dealing with these high values. And so we could also write this as 13.8 kilojoules. So either of those would be an appropriate answer. As we're then looking at, is this a endothermic or an exothermic reaction? Well, the water is being heated, and so that heat energy is going into the system. So this is an endothermic process. All right. Number 2. How much heat is released if 10 grams of aluminum cools from 55 degrees Celsius to 22 degrees Celsius? The specific heat of aluminum is 0.900 joules per gram times degrees Celsius. And so as we're looking at this, what are the things we're given? Making sure we are organized. This is for aluminum. And so our C value is for that aluminum, that specific heat. And then change in temperature is temperature final minus temperature initial. And so how much heat is released? Well, released means heat is leaving, and so we should expect a negative answer, and that's what we're looking for. If 10 grams, so we have 10 grams as our mass, of aluminum cools from 55 to 22 degrees Celsius. So final temperature is 22 degrees Celsius minus that initial temperature was 55 degrees Celsius. And so when we do that 22 minus 55, we get a negative 33.0, one digit after the decimal for sig figs, as our delta T. And that negative change in temperature is going to match with that negative Q value. And so the direction of our temperature change is telling us the direction of that heat. Is it moving in or out through this process? And then that aluminum, we were provided the specific heat. And we can see that we've got grams, degrees Celsius. Our answer is going to be in joules because that is the energy unit in our constant, and then we can go and plug these into our formula. You're welcome to abbreviate mass with lowercase m. I didn't on the formula sheet because little m is molality, but you are welcome to if you know what it means and you're just trying to save yourself a little bit of writing. All right, I didn't put my units in with this here, but those units would cancel just like they did on example 1. So that mass times our specific heat times change in temperature means we get negative. When we multiply those together, negative 297 joules would be our Q value. Looking at sig figs, 3 sig figs, 3 sig figs, 3 sig figs. And so that is, I rounded that to the nearest whole value or whole number. And our unit of joules is capital J as that abbreviation after our value. And so as we're looking at this, well, our aluminum is cooling, which means that that heat is leaving the system. So that is an exothermic, or this is an exothermic process. All right, example 3. The temperature of a piece of copper with a mass of 95.4 grams increases from 25 degrees Celsius to 48 degrees Celsius when the metal absorbs 849 joules of heat. What is the specific heat of copper? So when we're looking at this, we still are looking at that heat. We have mass. We've got C, and because the substance we're looking at is copper, and then delta T is final temperature minus initial temperature. And so as we kind of look at what we have, the temperature of a piece of copper with a mass, so we have our 95.4 grams, is increasing from 25 to 48. So 48 degrees is our final minus that 25 degrees. And so our delta T is positive 23.0 degrees Celsius. When the metal absorbs 849 joules of heat, well, absorbing is positive, so positive 849 joules. And you'll notice again that we've got a positive Q and a positive delta T. So those are going to match our mass and our C value. Those don't have a sign or a positive or a negative value to them. And then we are looking for that specific heat of copper. And so as we're looking at that formula, Q equals mass times C times delta T. If you want, you can go ahead and reorganize this before you plug everything in, divide by mass and delta T to get an expression over here that is going to equal C. So if you want to rearrange your equation before you plug things in, you can do that, or you can plug those in. So we've got that 849 equaling 95.4 times C times that positive 23. And so we can solve for that C value. So these are connected through multiplication. The opposite of multiplying is dividing. So let's divide both sides by 95.4. And then, so those cancel. And then we will also divide both sides by 23. So those cancel. And then we will get the C specific heat of copper when we do 849 divided by 95.4 and 23. And I get 0.3869. And then that continues. Let's look at our sig figs. We've got 849 is 3 sig figs, 95.4 is 3, 23.0 is 3. So we're going to keep our 1, 2, those 3 places. So we'll have 0.387. And then our units, as we look at our units, we've got joules, we've got grams, we've got degrees Celsius. And so our unit is that joules per gram times degrees Celsius. for that specific heat of copper. And that then this is, if we're looking at it, the specific heat would be the same whether this was endothermic or exothermic. But in the case of that heat being absorbed, that means that this is an endothermic process in this example. All right, so for number 4, this one's kind of a two-step. Iron has a specific heat of 0.446 joules per gram times degrees Celsius. When a 7.6 gram piece of iron loses 10.33 joules of heat, what is the change in temperature? So that's the first part. Finding delta T, that will be similar to what we did here, but finding that delta T. Go ahead and try that on your own, and then come back and we will do the second part together. All right. And now once we go through and find that first part, what is the change in temperature? Well, we found the change in temperature was negative 3.1 degrees Celsius. The heat is being lost, so this is exothermic. And then what is the initial temperature? Well, we have that delta T. We were told also that the final temperature is room temperature, so we can then use both of those to find that initial temperature. So our delta T equation here, delta T is final minus initial temperature. We're looking for initial temperature. And so I can go ahead and plug in those things that I have. I have negative 3.1 is my delta T. I'm plugging that in from here. That's going to equal T final is 22.0 minus T initial, and I need to just solve this equation for my TI. Having that minus T initial is a little funky, so if you want, move that over there, or you can just divide by a negative at the end. So we get temperature initial minus 3.1 equals 22 degrees Celsius. And then we can add 3.1 to both sides. With that adding, they both have one digit after the decimal, so we're going to keep 25.1, and then degrees Celsius, that's that initial temperature. So just a little extra step here of having to solve for that initial temperature. If you don't need to go ahead and set this up, if you can just think 22 minus what is going to give me that negative 3.1, you can also kind of do that mental math if that is something that clicks for you. All right, there is a specific heat worksheet for you to use as practice. Please reach out to your teacher with any questions.